Okay, continue with the cosine transform. So the concept is the same, where you will use different basis image. Okay, so cosine okay. So this is the formula to generate the basis image for cosine transform. So I just want to show you that how complex the cosine transform is, okay, compared to the WHT, which involve only +1 and -1. Okay, so if cosine and Fourier, so the basis can be in a variable. For example, the Fourier, the basis can be -g, +g. So the complexity is there. So cosine is used in image and video compression algorithms such as JPEG, MPEG, H.263. Okay. So although it is a complex, but it's giving better, okay, compared to WHT. So this is the basis of cosine. Okay. So you can generate a basis from 1D. Okay. So this is the, okay. So next is separable properties. Okay, if you notice what we have done before, we will do the transformation based on the IRC with the basis image. So the basis is in a matrix. So what is here is where you will use the vector as the basis image. Okay, where you only have vector. Vector means it is 1D compared to basis image. So all the three transform, what we have discussed earlier, have separable properties as well. Okay, separable properties means you will generate the basis image based on the separable properties, which is 1D transform. So if a 2D transform is separable, then the result can be found by successive application of two 1D. Okay, means you will have two 1D to generate the 2D transform. So this means that we can perform 2D transform using only 1D basis vector as well. Okay, means that you no need to generate the 2D transform, okay, from the 1D transform. Okay, but you can directly, okay, without having to generate the 2D basis images. Okay, for example, you have a 2D WHT, okay, on 2 times 2 image using only the 1D basis vector. Okay, so there are 2 points WH basis vector as follows. So this is WHO, which is this is the basis, and this is the WH1. This is the basis vector. Okay, with this input image, which is the RIC, you will perform the 1D WHT on each row or column, where you will perform the inner product between the basis vector and the image row. For example, okay, so this is the IRC, the input. This is the basis, okay, where you have 1D vector, basis vector for WH0 and WH1. So in separable properties, what you will do the inner product as well, but based on the 1D basis. Okay, so since the basis is 1 over 2 squared, then you will separate it, and 20 multiplied by 1 and 30 multiplied by 1. 20 multiplied by 1 and 30 multiplied by 1. Next, go to the next row, 40 multiplied by 1 and 50 multiplied by 1. Then you will get this one. You will get this one. So next 20 multiplied by 1 plus 30 multiplied by 1, then 20 multiplied by 1 and 30 multiplied by -1. We will apply the second vector, okay, on the same IRC. Next 40 multiplied by 1 plus 30 multiplied by -1. Okay, then you will get this one. Okay, so in separable properties, you have to do both. Okay, this one row followed by column. Okay, so output from this, you will apply the same basis vector, but it is in a column wise. Okay, so this is the output. Then with this, so you will have a 1 squared 2 and the basis squared 2. So you will, the output is already squared 2 and the basis is squared 2. So you have to multiply, okay, both. So for this, next 50 multiplied by 1, 90 multiplied by 1. Okay, 50 multiplied by 1, 90 multiplied by -1. Then -1 multiplied by 1, -10, -10, not -1, -10 multiplied by 1. -10 multiplied by 1 and -10 multiplied by -1. Okay, so first you will do row. Second, you will do the by column. Then you will get this one. Okay, so the result will be this. So you simplify, so you will get this one. So you can verify that the result is the same as in using 2D Walsh-Hadamard basis image. So you can try, okay, using the same basis image, okay, with plus 1 and plus 1 -1 for the matrix, okay, basis image, which apply to the IRC. This is the IRC. Okay, so it can be either you use separable properties where you do the transformation, okay, row by row followed by column, or you can do the same, okay, using the same basis matrix, okay, to apply both apply IRC. So you will get the same example. So the advantage of this method is that it requires less computation, okay, compared to the matrix. Okay, as a conclusion, so interpretation of transform image. Okay, the transform image represents the intensity of various spatial frequency. Okay, it is not like a spatial domain where you can see what is the what is in the image. But if you transform, it will only represent the intensity of the various spatial frequency. So for WHT and CT, the top left corner of the transform image is associated with 0 frequency, which we call is DC. Okay, and the rest will be the AC. So the transform coefficient represents higher and higher frequency as it goes from top left to bottom right of the transform image. Means you will have an image. So this is the top high, okay, and the rest will be the left to bottom right. By knowing what the transform image represent, we can perform filtering operation in the frequency domain to modify the image according to our needs. Okay, that's all. Thank you.